All right, welcome everyone to another deep dive. Today we're going to be really zeroing in on NVIDIA and sort of where they're headed as we look out towards 2025 and beyond. And we're basing all of this on what came out of their recent GTC conference. Now, to help us make sense of it all, we're joined by Llama from Llama Tech Trends. They're a machine learning engineer based out in Singapore. And Llama, thanks so much for joining us. I know GTC, there's like a fire hose of information coming out of that thing every year. So I really appreciate you kind of taking the time to distill it down to what really matters for folks like us who want to get up to speed quickly.
Yeah, it's funny you should say fire hose. I was just talking to somebody else and they said it's like drinking from a fire hose, right? GTC.
So
So many announcements, so much going on, so much deep technical stuff that, unless you're like really in the weeds, it can be hard to kind of parse through it all. And I think what's really interesting too is this year really highlighted the shift that NVIDIA has been making, where they're really focusing on their server business and specifically like these big CSP vendors, right? Like your Amazon Web Services, your Google Clouds, your Microsoft Azures. Like these are the companies that are like really driving so much of the demand for NVIDIA's latest and greatest chips.
Yeah, and that was super apparent from Jensen's keynote, right? It was like, it's not even just the majority of their business anymore. I think Llama pointed out that it was like 70% of their revenue is coming from these server orders from these cloud providers. So that's what we want to focus on today. We want to kind of cut through all of the noise and figure out like, what are the core technical innovations? What are NVIDIA's advantages and where are they headed in, the coming year or so in this really critical part of the market?
Absolutely. And, it's not just about like how many teraflops or petaflops these GPUs can crank out. I mean, that's obviously important. But what Llama really highlighted for me was that there's this fundamental truth that you have to kind of grapple with in GPU computing. And it's that the speed of the calculation itself often isn't the primary bottleneck.
Oh, that's interesting. Well, we always hear about like, oh, this is so many times faster than the previous generation, right?
Right. But it's like, imagine you've got this, Formula One race car, but it's stuck in like rush hour traffic, right? It has all this potential, but it can't actually go anywhere fast. It's funny, the former CEO of Intel, he had this great analogy for GPUs. He called them like the world's most expensive memory controllers. And I think that really captures the essence of what we're talking about here.
Okay, the world's most expensive memory controllers.
Yeah.
So to understand that, I guess we really have to kind of break down how data actually flows within a GPU system, right? I mean, it's not just like the processor sitting there crunching numbers all day.
Right. So like Llama laid it out.
Yeah.
You've got your data starting way back on the disk, right? Your hard drive or your SSD.
Terabytes and terabytes of data.
Exactly. Then it moves into the CPU's main memory. Now, this is where things get interesting because unlike CPUs that, share the system memory, GPUs have their own dedicated high-speed memory. It's called VRAM. This is super critical for rapid access to all that massive data. So you might have, 40, 60, 100 gigabytes or even more of VRAM on these high-end AI cards. From there, the data gets transferred to these super fast little on-chip caches called L1 and L2. And then finally, you've got the registers where the actual number crunching, the calculations actually happen.
Okay, so it's like a multi-stage journey for the data to get to the point where it can actually be used, right?
Exactly. And what's fascinating is the huge difference in scale, right? You've got terabytes on the disks, gigabytes in the memory, but those L1 and L2 caches, they're tiny. We're talking kilobytes. And that, as Llama pointed out, is where the bottleneck often arises. A significant portion of the GPU's time is spent just waiting for the data to be fetched from those larger, slower memory banks. So if you want to understand NVIDIA's priorities right now, this is like ground zero, right? Understanding how to optimize this entire flow of data.
That makes perfect sense. So that brings us to, I guess, the first major trend that Llama identified, which was this idea that NVIDIA is laser focused on optimizing both the memory architecture and the performance of how that data gets transmitted, right? Because like you said, if you've got the world's fastest processor, but it's starved for data, then, it doesn't matter, right?
Precisely. It's all about feeding the beast, right? And this leads right into the second trend that Llama highlighted, which is the speed and efficiency of data transmission between devices. Now, this isn't just about the CPU talking to the GPU, right? It's about, in the context of modern AI, how do you get GPUs talking to each other super fast? Especially when you consider these huge weight files, right?
Yeah.
In these large language models that everybody's talking about, and the need for longer context windows. All of that requires, passing huge amounts of data between GPUs in a very coordinated way.
Yeah, and I think Llama was really emphasizing the difference between training these models and then using them for inference, right? Because when you're training, you're constantly having to average the learnings across all these different GPUs. But then, when you're doing inference, especially with things like mixture of experts architectures, where you're essentially calling on these specialized expert models that might reside in different GPUs, the communication becomes even more critical, right?
Yeah, it's like trying to conduct the symphony orchestra where all the instruments are spread out across different rooms, right?
Right.
You need that perfect timing, that perfect coordination. And what's amazing here is that NVIDIA recognized this as a bottleneck very early on, and they went and developed NVLink.
Right, NVLink. So before NVLink, I guess the main way to connect things was PCI Express, right? PCI, you think?
Right, exactly. But PCI Express, while it's a great general purpose interface for all sorts of peripherals, it just wasn't designed for this kind of intense, high bandwidth communication between GPUs that are working on these massive data sets.
So how much faster is NVLink?
It's not even close. Like
Okay.
Llama
Yeah.
gave us some numbers. PCIe early on was like 20 gigabytes per second. NVLink 3.0, even back in 2020, was hitting like 600 gigabytes per second with multiple links. And it's only gotten faster from there.
Wow, that is a huge difference. So NVLink is essentially allowing these GPUs to bypass the CPU altogether, right?
Yeah.
And just talk directly to each other.
Exactly. Before you might have a situation where data has to go from one GPU back to the CPU and then over to another GPU, it's a huge time penalty. NVLink creates this super fast highway directly between the GPUs.
And they haven't slowed down, right? They've kept pushing it further.
Absolutely. Llama told us about NVLink 5.0 now. It's in their new Blackwell GPUs. That's pushing something like 1,800 gigabytes per second. And there's even talk about a new version in 2026 that could be another 50% faster. So they're clearly not messing around with this interconnect stuff, right? It's fundamental to their whole strategy. I mean, think about it. This level of communication opens up the possibility of training even larger, more complex AI models at speeds that we just couldn't imagine even a few years ago.
Yeah, it's like unlocking a whole new level of possibility. And I guess this ties in with NVIDIA's, product strategy as well, right? With how they're increasingly bundling their CPs and GPs together.
Right, exactly. Llama pointed out their GB series and the new Blackwell chips. They're often sold as these integrated units, like those NVL72 racks. You get 72 GPUs, all interconnected with NVLink. It's very much a focus on vertical scaling. It's about maximizing the compute power and the communication within a single, incredibly powerful node.
So it's like building these, these super dense compute clusters, like, within a single racks.
Exactly. They're creating these highly optimized little compute universes. But then, of course, you also need to think about scaling horizontally, right? Connecting multiple of these nodes together. And that's where things like NVIDIA's InfinityBand technology come into play, which provides that high-speed fabric for linking these massive multi-GPU systems together.
So it's like, cities connected by high-speed rail. Each city is like one of these super nodes, right?
Perfect analogy. But it's not all just NVIDIA, right? Llama did mention this interesting potential competitor in the interconnect space called UALink. It's from a company called Synopsys, and their pitch is that it's a more universal standard designed to connect not just GPUs, but various types of accelerators, maybe FPGAs or other specialized AI chips.
So it's kind of like an open standard then, right, for anyone to use.
Yeah, that's the idea. But here's the thing. Synopsys, they don't actually make chips themselves. They provide the IP, like the blueprints for other companies to build into their chips. So while it has this potential to enable, these multi-vendor interconnected systems, Llama was also very clear about the timeline. The IP spec itself isn't expected until late 2025. So we're talking about actual chips, maybe by the end of 2026, and full rack level systems probably not until mid-2027. So that's a pretty significant lag compared to where NVIDIA is right now with NVLink, which is a mature, evolving technology that's already baked into their current and next-generation hardware.
Yeah, it makes you wonder if UALink can really catch up. I mean, NVIDIA has this enormous head start. And this whole interconnect thing, it seems so fundamental to the future of AI infrastructure. I mean, for folks listening, think about the implications here, right? These choices in interconnect technology are going to determine how quickly and efficiently we can train and deploy these increasingly complex AI models. So it's a pretty big deal.
Absolutely. And that kind of brings us to the third trend that Llama highlighted, which is all about software optimization, specifically NVIDIA's CUDA platform and this interesting new development called the Tile model.
Oh, yeah, Tile. I saw some headlines about that.
Yeah, so NVIDIA has been making a big push to make parallel computing, more accessible to a wider range of developers. And a big part of that is, they're moving towards deeper integration with Python, which has become the dominant language for AI and machine learning. Traditionally, CUDA programming was more C++ heavy, which, can be a bit of a hurdle for some folks. So Python integration, it's a big deal for lowering the barrier to entry.
So it's like they're trying to meet developers where they are, right? Make it easier for people to actually utilize the power of these GPUs.
Exactly. And then this tile model is really intriguing. Basically, it's all about efficiency. It's about allowing multiple applications or tasks to run on the GPU with a single read and write operation to the memory. So instead of constantly loading and unloading data for each little computation, you load it once, do all calculations across these different tiles, and then write it back. It's like batch processing on steroids, right?
It sounds like a pretty clever optimization. I mean, if you're running a bunch of smaller tasks, this could really streamline things, right?
Exactly. And it's not just about the raw compute, right?
Right.
Llama also pointed out this trend of tighter integration with things like OLA's Triton. Either Triton itself or Triton-based applications being integrated into frameworks like PyTorch. And this is all about optimizing specific types of computations that are very common in these large language models, like transformer operations.
So there's this kind of two-pronged approach, right? Optimizing the hardware and the software in tandem. It's not enough to just have the fastest chips. You need the software ecosystem to take full advantage of it.
Absolutely. And what's also really interesting is this growing focus on how these massive clusters of GPUs actually operate together, right? Llama was talking about this need for more robust, fault-tolerant mechanisms. I mean, imagine you're training a model for days or weeks on end, right? What happens if a GPU fails in the middle of that? Ensuring reliability and uptime in these massive distributed systems is a huge challenge. So there's a lot of interesting work being done on the software side to address that.
Oh, that's fascinating. So it's not just about making individual GPUs faster, it's about making sure that the entire system can operate reliably at scale, right?
Exactly. And by the way, for those of you who are developers, that CUDA tile model is expected to be released and open sourced around the middle of this year. So definitely something to keep an eye on.
Okay, excellent. So the next trend that Llama highlighted was something called unified memory architecture, which, to be honest, I'm not super familiar with.
So the basic idea is that the CPU and the GPU can directly access and share the same pool of memory, right? So potentially eliminating the need for all this explicit data transfer back and forth between them.
Okay, so it's like breaking down the wall between the CPU and the GPU, right? Making it a more seamless experience for the data.
Exactly. And Llama pointed out that Apple's been doing this for a while now in their Macs, right? They have this unified memory architecture. But for NVIDIA, it's been more of a feature in their high-end, like industrial server products, not so much in your, RTX or GTX gaming cards that, a lot of folks might have in their PCs.
Right.
But then one of the really interesting announcements from GTC was this DGX Spark. Llama described it as this kind of smaller, self-contained AI workstation. It has over 100 gigabytes of VRAM, which is impressive on its own. But the key thing is that it uses this unified memory architecture, the same one that's in those, high-performance GB series GPUs.
Wow, so they're bringing that technology down to, a more, I guess, accessible form factor, right?
Yeah, it seems like they're initially targeting it at, research units and individual AI practitioners, give them this powerful local machine for development and experimentation. But it does raise this question, right? Like if DGX Spark takes off, could we see unified memory become more mainstream? Like could it make its way into AI PCs down the line? It's definitely a thought-provoking development.
Yeah, it'd be interesting to see if that, trickles down to the consumer space eventually. So trend number 5, we're talking about the future GPU memory itself, right?
Yeah.
Specifically high bandwidth memory, HBM, and even things like in-memory computing, which sounds super futuristic.
Yeah, so HBM, as Llama reminded us, has been around for a while. NVIDIA's been using it in their high-end GPUs since, the Pascal architecture. But its importance is growing exponentially, right, as these large language models just keep getting bigger and bigger. And he really hammered home this point about the massive difference in scale between VRAM, which is measured in gigabytes, and the L1 and L2 caches, which are measured in kilobytes. And to process these huge models, the GPUs have to break those weights down into tiny little chunks that can fit into that fast on-chip memory.
So it's like you've got this giant library full of books, but you can only fit a few pages through the door at a time.
That's a great way to put it. And then there's this more radical idea that the former Intel CEO was talking about in memory computing.
Yeah, that sounds wild.
Right. The idea is that you'd actually perform the computations directly within the memory chips themselves. So you wouldn't have to move data back and forth between the processor and memory. It would be a fundamental shift in how computers work.
I mean, that sounds incredibly efficient, right?
Hmm.
If you could eliminate all that data movement. But I imagine it's also incredibly complex to engineer.
Absolutely. But Llama's point here is that innovation in memory technology, not just like raw capacity, but these kind of more fundamental architectural changes, is going to be a huge focus for NVIDIA moving forward.
Okay, makes sense.
Yeah.
So the last trend that we wanted to touch on was something that I found really intriguing, which was the potential for NVIDIA to get more involved in the ASIC market, right? Application-specific integrated circuits.
Right. And this is where things get really interesting. So the argument for ASICs and AI is that for certain workloads, especially inference, actually using the trained AI model, you could potentially get much higher efficiency and lower cost compared to using these general purpose GPUs.
So it's like, if you're building a house, general purpose hammer is great, but if you're doing a very specific task, like putting in nails, a nail gun is going to be way more efficient.
Exactly. And that's kind of what the former Intel CEO was arguing, right? He was saying that while GPUs are great for the heavy lifting of training these models, eventually we might need something much more power efficient and cost effective specifically for inference. And ASICs could be the answer.
So why wouldn't NVIDIA jump into that market, right? I mean, it seems like a natural fit.
Well, Llama pointed out some risks. The big one is that once you design an ASIC, it's fixed, right? It's optimized for a very specific task or even a specific model architecture. And with the pace of innovation in AI, new attention mechanisms, new architectures, like mixture of experts popping up all the time, there's a real danger of locking yourself into a design that could quickly become obsolete.
Yeah, it's like betting on the wrong horse, right?
Mm-hmm.
If you put all your chips into an ASIC that's optimized for a particular model architecture, and then suddenly a new architecture comes along that's way better, you're kind of stuck.
Exactly. So the big question is now the right time to go all in on ASICs, given how much the AI landscape is still changing? And even if you do go the ASIC route, as Llama pointed out, you still need to think about communication, right? You might have multiple ASICs working together. So those interconnect technologies like that UA-Link we talked about, they're still going to be important even in an ASIC-dominated world.
Yeah, that makes sense. But then there was this really interesting piece of news that Llama shared, right? About MediaTek.
Yeah, so MediaTek, they make all sorts of chips, including ASICs, and they've acquired patents related to NVIDIA's NVLink technology. So this could potentially open up a scenario where MediaTek could design chips, maybe for AWS or other cloud providers, that could directly connect to NVIDIA GPUs using NVLink.
Wow, that's a pretty significant development. I mean, it kind of hints at this possibility of, a more diverse ecosystem of chips, all interconnected with NVIDIA's technology.
Exactly. And it raises the question of how NVIDIA might respond, right? Will they develop their own ASICs? Will they partner more closely with companies like MediaTek? It's definitely something to watch closely.
Yeah, fascinating stuff.
Yeah.
So to recap, I mean, we've covered a lot of ground here. We talked about, the importance of memory architecture and data transmission, how NVIDIA has been pushing the boundaries with NVLink, the software optimizations they're making with CDA and that new tile model, the potential of unified memory to change how we think about system architectures, the evolution of GPU memory with HBM, and even more radical concepts like in-memory computing, and then finally this whole question of ASICs and how NVIDIA might play in that space. It's clear that NVIDIA is really focused on this server market, and a lot of their innovation is being driven by the demands of these big cloud providers.
Absolutely. I mean, they're clearly in the driver's seat right now when it comes to, providing the hardware that's powering the AI revolution. But it's a rapidly evolving landscape, and it's going to be fascinating to see how things play out over the next few years.
Exactly. So here's a final thought for everyone listening. Given all of this rapid innovation, both on the hardware and software side of AI, what do you think is going to be the biggest bottleneck? 3 years from now, will it be compute power? Will it be memory capacity and speed? Or will it be the ability to move data efficiently between all these increasingly powerful processing units? Let us know what you think. And thanks for joining us for another Deep Dive.
Thanks for having me.